So in part one, we saw the VDS, that's the voltage across drain and source, has to be greater than V over drive. And V over drive is the difference between the voltage across gate to source minus the threshold voltage of the transistor, which is a turn-on voltage. Having said that, we are now going to evaluate the voltages and the currents based on these biasing conditions. So you see the R1 and R2 are 5K each. The voltage is produced at the drain pins of both the transistor Q1 and Q2 are about 2.1 volt. So you can essentially calculate the current through the transistors, which are the drain currents of the transistor. So we can say that ID will be equal to V plus minus VO. Remember here, VO1 is equal to VO2 is equal to VO. I said that divided by the value of resistor R. So R1 is equal to R2 is equal to R. So we say that this is 3.3 volts minus 2.1 volt divided by 5 kilo ohms. So it is about, let me calculate, this is 1.2 volt divided by 5K. So approximately how much that comes? Let us write that. Approximately 0.3 milliampere. It is like that. So let me write here 0.3 milliampere. Now that current is your source currents. That is your IS here and IS here. So we'll say that IS1 is equal to IS2 is equal to ID1 is equal to ID2 is equal to 0.3 milliampere. And ISS is your 500 microampere. Now, that is a question. So if you have like 500 microampere source current, which is fixed here, then IS and IS1 and IS2 should be about 250 microampere. So it's about 300 microampere approximately, right? So we calculated it 0.3 milliampere, which is equal to about 300 microampere. And this current, if we have set here, then the ID will be about 250 microampere and IS will be also 250 microampere. In that case, your voltage, so the current has to go down, then the voltage here will also go down. So it will be about not 2 volts, but rather it will be about, let's say 2 voltage, 2 volt here, 2 volts here. Then only you can have the ID, the currents about half of this one. So ISS is equal to 2 times the IS. And now you have this negative voltage supply of minus 3.3 volt. Here at the common source pins of the transistors, you have the voltage of about 0.26 volts, about 266.7 millivolts. All right, it is the same potential at this node. So now source pin is at 266.7 millivolt, gate pin is at 1 volt. So what would be the VGS? VGS would be VG minus VS, which would be 1 minus about 0.266 volts. So it can be about 0.733 volts. So that's the voltage VGS. So the threshold voltage has to be less than VGS has to be greater than your VTH, then only your transistor will enter into conduction. And after the channel is formed, your VDS has to be greater than the drop, the difference between VGS minus VTH. Then only your transistor will operate in a saturation region, which we explained in our previous module. So if you are new to this channel, refer to the previous module. We'll get that. Now, what is the voltage across the drain and the source pins of the the drain and the gate pins of the transistor. So let me write here, that is VDG would be difference between VD minus VG. VD is at 2.1 volt minus VG 1 volt. So it is about 1.1 volts. That is it. What about VDS? VDS will be VD minus VS. It is 2.1 volt, or we could set that this is not 2.1 volt, this will be 2 volt if the ID has to be half of the ISS. So let's assume 2.1 volt minus VS is at about 0.66 0.266 volts. So that's about 1.859 volts, something like that. Okay, so now you calculate, assuming if we say if VTH is equal to 0.5 volts for each transistor, then the overdrive voltage VGS we just calculated is about 0.7. So V overdrive will be 0.73 minus 0.5. So approximately, let's say 0.2 volts. And what is the VDS? VDS is 1.859, which is greater than 0.2 volts. Therefore, you can say, okay, the transistor can operate in the saturation region. That's how you choose the biasing condition. If those conditions are not met, you can adjust the W/L ratio of the transistor. So this is how you actually can solve the DC biasing conditions, and then you apply the differential inputs or the common mode input to analyze the performance of your circuit. So we have so many videos using SPICE circuit simulator, so you can try it as an exercise, choose the value of W/L and then simulate the circuits. So if you have some comments, write in the comment section. If you like the video, click the like button, subscribe to our channel, and stay tuned for more informative videos like this. Till then, wish you happy learning.